For most of human history, reason was treated not merely as a tool, but as a promise. The promise that the world, no matter how mysterious, could eventually be made clear, that every phenomenon hid a structure, that every question, if pursued long enough, would yield an answer. This faith in reason shaped civilization, sciences, and identities. It told us that the universe was not arbitrary, not hostile, not unknowable, only complicated. And for a long time, this belief appeared justified. From the motion of planets to the mechanics of engines, from the circulation of blood to the propagation of light, reason delivered miracles. It transformed chaos into law, uncertainty into prediction, mystery into method. The universe began to look like a grand machine, intricate but intelligible, operating according to rules that the human mind could uncover. But beneath this success lay an assumption rarely examined, that reality itself was logically structured in a way compatible with human thought. That assumption is now quietly collapsing, not with a dramatic crisis, but with accumulating failures. Small fractures first, discrepancies in experiments, models that worked only within narrow limits, predictions that decayed rapidly with scale. At first, these were treated as technical problems. More precise instruments would fix them, larger datasets would smooth them out, more powerful mathematics would eventually close the gaps. Instead, the gaps widened. The first public warning came from physics. Quantum mechanics did not merely challenge common sense, it undermined the foundations of causality itself. Particles existed in multiple states at once. Effects appeared before causes. Measurement altered what was being measured. These were not philosophical speculations. They were repeatable facts. To preserve logic, physicists redefined it. Probability replaced certainty. Observation replaced objectivity. Reality became conditional on interaction. The universe could no longer be described independently of the act of knowing it. Yet this was framed as a special case, a strange corner of nature where intuition failed, but reason still ruled, if carefully reformulated. That comfort did not last. As science turned toward complex systems, reason encountered a deeper resistance. Climate models diverged unpredictably. Neural networks produced results no one could interpret. Biological systems rewrote their own regulatory rules under stress. Social systems displayed collective behaviors that could not be traced back to individual intentions. These were not errors. They were stable phenomena. Systems whose behavior could be observed, measured, and reproduced, but not derived. Here, reason faced a new kind of obstacle, not randomness, not noise, but organized patterns without transparent causation. Emergence, the word chosen to name this failure, was polite. It suggested novelty arising from simplicity, but in truth, it marked a limit. Higher-level laws that could not be logically deduced from lower-level rules. Consciousness from neurons, intelligence from circuits, order from turbulence. The old dream that by understanding the parts we could understand the whole began to fail. And with it, the deepest ambition of reason, total explanation. The crisis intensified when prediction, reason's final defense, began to collapse. In classical science, explanation and prediction were inseparable. To understand a system meant to foresee its future. Newton's laws predicted planets. Maxwell's equations predicted waves. Mendelian genetics predicted inheritance, but modern systems refused to cooperate. Weather forecasts decayed into chaos within days. Economic models performed little better than intuition. Epidemiological projections collapsed under real-world complexity. Even physical simulations required constant correction to remain stable. The problem was not ignorance, it was sensitivity. Tiny differences in initial conditions produced wildly different outcomes. Feedback loops amplified noise into structure. Nonlinear interactions rewrote trajectories faster than computation could track. This was chaos theory's revelation, determinism without predictability. A system could obey strict laws and yet be practically unforeseeable. But an even darker realization followed. Some systems were not merely unpredictable, they were computationally irreducible. No shortcut existed, no formula could replace simulation. The only way to know what they would do was to let them do it. This shattered the old belief that reason could, in principle, compress reality into understanding. Explanation became after-the-fact description. Prediction became probabilistic guesswork. understanding became operational convenience. And yet publicly, the language of mastery remained. Scientific papers continued to speak of models, mechanisms, and laws. Universities continued to teach logic as the skeleton of nature. Textbooks preserved the image of a rational cosmos awaiting discovery. But in research rooms and closed conferences, a quieter tone emerged. Many now admitted what they could not publish. That explanation was receding, not advancing. That the more data we collected, the more structure appeared, and the less interpretable it became. Artificial intelligence made this contradiction unavoidable. Neural networks learned patterns no human could follow. They solved problems using internal representations no one could decode. Their success did not depend on understanding, only on performance. For the first time, humanity possessed systems that reasoned effectively without reasoning transparently. Black boxes replaced theories. Accuracy replaced explanation. Prediction divorced itself from comprehension. This was not a technical shift. It was philosophical. If a machine can predict without understanding, then prediction is not evidence of truth. If a model works without explanation, then explanation is no longer necessary for control. Reason, once the gateway to power, became optional, and with that, its authority weakened. A deeper question began to haunt the foundations of inquiry. What if the universe itself is not logically compressible? What if no finite system of principles can fully reconstruct it? This possibility, once dismissed as mystical, now appears mathematically plausible. Gödel proved that any sufficiently powerful logical system contains true statements it cannot prove. Turing showed that some problems are undecidable by any algorithm. Chaitin demonstrated that randomness is built into the fabric of formal systems. These were not physical results. They were structural limits of reasoning itself. Together, they imply something unsettling. That incompleteness is not a temporary failure, but a permanent feature of rational systems. If logic cannot close itself, how can it close the universe? The final blow comes from an even more disturbing angle: evolution, human. Reasoning did not evolve to discover truth. It evolved to survive. It compresses reality into heuristics. It seeks causality even where none exists. It prefers simplicity even when complexity dominates. It constructs narratives to reduce anxiety, not to maximize accuracy. Our sense of logic may be a local adaptation, effective at human scales, dangerously misleading beyond them. If this is so, then the collapse of explanation is not a crisis of science. It is a revelation of mismatch. The universe may operate by principles fundamentally alien to human intuition, not illogical, but non-translatable. At this boundary, reason does not fail dramatically. It simply stops yielding insight. We can still measure, still manipulate, still predict in limited windows, but understanding, in the deep sense, evaporates. We become technicians of patterns we do not comprehend, engineers of forces we cannot explain, observers of regularities whose origin remains closed, and perhaps this is the final. Unspoken fear behind the silence. Not that logic is broken, but that reality was never designed to be understood. That clarity is not a universal right. That knowledge has a horizon, beyond which there is only behavior, not meaning. The moment reason stops explaining reality is not the end of science. It is the end of innocence. From here on, inquiry becomes navigation, not conquest. Models become maps, not mirrors. Truth becomes layered, provisional, and forever incomplete. And the universe, once imagined as a grand equation waiting to be solved, begins to resemble something far more unsettling. A system that allows itself to be used, but never fully known. The first sign that reason was losing its grip did not appear as chaos. It appeared as order. Across laboratories, simulations, and datasets, researchers began to encounter patterns that were undeniably real, yet strangely hollow. Structures repeated with precision. Correlations emerged with consistency. Systems behaved in stable, reliable ways. And yet, when scientists asked the most important question, why, the answer refused to arrive. At first, this seemed like progress. After all, the history of science is filled with discoveries that began as mysterious regularities. Kepler mapped planetary orbits before Newton explained them. Mendel charted inheritance before DNA was known. Pattern had always preceded theory, but something different was happening now. These new patterns did not invite explanation, they resisted it. In physics, condensed matter systems produced phases whose behavior could not be derived from the equations governing their particles. In biology, gene networks stabilize themselves through feedback loops no single gene controlled. In neuroscience, brain activity organized into rhythms and assemblies that could not be traced back to individual neurons. The data was clean, the repetition undeniable, the cause absent. Researchers called this emergence, but the word concealed more than it revealed. It suggested that complexity naturally produced novelty, as if explanation had merely not caught up yet. But with each decade, the same phenomenon reappeared across domains, unchanged by deeper measurement or better mathematics. Higher-level order arose that was not logically contained in lower-level rules. The old reductionist dream, that the whole is nothing but the sum of its parts, quietly collapsed. What replaced it was something more disturbing, systems whose behavior was lawful but not derivable. They obeyed rules, but not rules we could write down. Nowhere was this more visible than in artificial intelligence. Neural networks learned to recognize faces, translate languages, diagnose disease, and defeat human champions. They did so by discovering internal representations, patterns of patterns, formed through exposure, not design. When engineers attempted to inspect these internal structures, they found no clear logic, no symbolic reasoning, no chain of causes, only vast numerical landscapes where millions of parameters interacted in ways no human could meaningfully trace. The system worked, but no one understood how. For the first time, prediction divorced itself from explanation. A machine could perform reliably while remaining conceptually opaque. This was not an accident. It was intrinsic. The more powerful the model became, the less interpretable it grew. Accuracy and understanding moved in opposite directions, and researchers accepted this trade without protest because it delivered results. But beneath the success, a profound shift had occurred. Science had begun to tolerate knowledge without meaning. Similar patterns emerged in economics. Markets displayed cycles and crashes that repeated across centuries and cultures. Bubbles inflated, collapsed, and reformed with haunting regularity. Statistical regularities governed volatility, distribution of wealth, and collective panic. And yet, no economic theory could derive these patterns from individual behavior. Rational agents did not produce rational markets. Small shocks produced massive crises. Major interventions produced negligible effects. The system behaved as if governed by its own hidden laws, laws not reducible to incentives, information, or utility. Again, the data was clear, the explanation missing. In ecology, food webs stabilized themselves through network structures no species controlled. In epidemiology, diseases followed waves shaped not only by biology, but by behavior, infrastructure, and perception, layers interacting in ways no single model could integrate. In each case, the same structure appeared. Multi-level systems whose global behavior could not be logically reconstructed from local rules. This was not randomness, nor was it ignorance. It was structural opacity. The most unsettling discovery came when researchers realized that these patterns were often optimal. Systems found efficient solutions without central control. Evolution explored viable forms at speeds that defied combinatorial logic. Ant colonies built transportation networks rivaling human engineering. Neural circuits solved optimization problems without symbolic reasoning. Efficiency appeared without planner. Design without designer. Order without derivation. Classical logic had no category for this. Optimization without calculation. Intelligence without representation. Learning without understanding. The universe, it seemed, was computing in ways alien to human thought. Some theorists proposed that nature itself performs a kind of distributed computation, that physical processes explore solution spaces faster than algorithms could. That emergence is not accidental, but computational. But this only deepened the mystery. If the universe computes, by what rules? If it optimizes, toward what objective? And if these processes outperform formal logic, then logic is not the ultimate language of reality. It is merely one of its dialects. A deeper fracture appeared when researchers tried to formalize these phenomena. Complexity theory classified systems by computational hardness. Many natural processes fell into categories known to be intractable. No algorithm could predict their long-term behavior efficiently. Not because we lacked cleverness, because mathematics itself forbade it. In these regimes, patterns exist but cannot be derived. Correlations appear but cannot be explained. Prediction is possible only locally, temporarily, approximately. This shattered the final illusion that explanation always trails discovery. In many cases now, explanation never arrives. The pattern is all we get. This forced a quiet philosophical reversal. For centuries, science sought laws. Now it increasingly sought models, flexible, statistical, empirical constructs that fit data without claiming truth. Deep learning, agent-based simulations, ensemble forecasting all emphasize performance over interpretation. The question is no longer, why does this happen? But, does this model work well enough? Truth is replaced by utility, meaning by accuracy, understanding by control. And control, ironically, often works. We manipulate systems we do not comprehend. We cure diseases whose mechanisms remain obscure. We stabilize networks whose dynamics no one can write down. We navigate complexity without a map. This success masks a deeper loss. When patterns cease to be explainable, explanation itself loses authority. The role of theory shifts from revealing structure to managing behavior. Science becomes an engineering discipline of black boxes. Reliable, powerful, conceptually blind. The human mind, evolved to seek causes and narratives, now confronts a universe that offers only correlations, not lies, but silence. And perhaps the most disturbing feature of these unexplainable patterns is their universality. They appear in matter, in life, in mind, in society. Across scales and substances, the same architecture recurs, layered systems producing lawful behavior without transparent causation. This suggests not an anomaly, but a principle. That reality is generative rather than deductive. That higher-order structure is not logically contained in lower-order rules. That explanation is not cumulative, and that understanding has an asymptote. The old dream imagined science converging toward a final theory, a single framework from which all phenomena could be derived. But unexplainable patterns undermine this hope. They imply that no final compression exists. That reality is not a theorem, but a process, forever unfolding new regularities that no finite logic can exhaust. In such a universe, knowledge becomes provisional, not because we are ignorant, but because the system itself outpaces representation. The rise of unexplainable patterns is therefore not a failure of method. It is a revelation of structure, a signal that the universe organizes itself through mechanisms deeper than human reason, not hostile, not mystical, simply indifferent to our demand for clarity. And so the crisis deepens, not because we lack data, not because instruments fail, but because the very success of science has uncovered its boundary. We can detect patterns, we can exploit them, we can even predict them, but we cannot always explain them. And when explanation collapses, something fundamental changes. The universe stops appearing as a book written in logic and begins to resemble something far more unsettling, a system that produces order without offering reasons. For centuries, prediction was the crown of reason. To explain a phenomenon was not enough. True understanding meant foresight. The scientist who could foresee eclipses, tides, harvests, or epidemics possessed not only knowledge, but power. Prediction separated superstition from science, narrative from law, intuition from proof. A theory that could not predict was dismissed as incomplete, if not meaningless. This standard shaped the entire architecture of modern inquiry. Newton's equations predicted planetary motion centuries ahead. Maxwell's laws foretold invisible waves before radios existed. Mendel's ratios anticipated inheritance long before genes were known. In each case, the future unfolded exactly as reason had declared. It seemed obvious that explanation and prediction were inseparable, but this unity is now quietly unraveling. Across disciplines, models once trusted to foresee the future now struggle to outperform randomness, not because of carelessness or ignorance, but because the systems themselves resist being predicted. The first fractures appeared in the atmosphere. Weather forecasting, once a triumph of physics, hit an invisible wall. Despite satellites, supercomputers, and oceans of data, forecasts deteriorated rapidly beyond short horizons. Tiny uncertainties in initial measurements exploded into massive divergences. Two simulations, nearly identical at the start, evolved into radically different storms. Chaos theory revealed the mechanism. Deterministic equations could generate unpredictable outcomes. The laws remained exact. The future did not. Here, prediction collapsed not from noise, but from sensitivity. A system could obey perfect rules and still be practically unknowable. This discovery shook more than meteorology. It implied that determinism does not guarantee predictability, that knowing the laws is not enough, that foresight can be mathematically impossible, even in a lawful universe. Other fields soon encountered the same wall. Economic forecasting, once confident in equilibrium models and rational agents, began to fail spectacularly. Financial crises erupted without warning. Market crashes defied consensus projections. Growth predictions diverged wildly from reality. Researchers improved data, refined assumptions, and expanded computational power. The failures persisted. The problem was not error, it was structure. Markets were not linear systems. They were networks of feedback, expectation, imitation, and fear. Small rumors triggered global panics. Large interventions produced negligible effects. The same models that explained yesterday's behavior failed tomorrow. In controlled experiments, some economic predictions performed no better than coin flips. More data did not rescue them. It destabilized them. The future, it seemed, adapted to being predicted. Epidemiology faced a similar reckoning. Models of disease spread, elegant and mathematically sound, collapsed when confronted with real human behavior. Compliance fluctuated. Policies altered contact networks. Perception changed transmission. Predictions diverged dramatically across models built on the same data. Some overshot catastrophically. Others underestimated fatally. In hindsight, many projections were not merely wrong, they were misleading. Yet the equations were correct, the inputs accurate, the computation flawless. What failed was not the machinery, it was the assumption that complex systems remain stable under prediction. This deeper problem soon acquired a name: reflexivity. In systems containing agents who respond to forecasts, the act of prediction alters the outcome. Markets crash because they are predicted to crash. Epidemics slow because they are forecast to accelerate. Policies fail because agents adapt. Here, prediction undermines itself. The more influential the forecast, the less accurate it becomes. This alone would complicate science. But an even darker limit soon emerged. Some systems were not merely chaotic. They were computationally irreducible. The concept proposed in theoretical computer science is devastatingly simple. For certain processes, no compressed formula exists, no shortcut, no closed-form solution. The only way to know their future is to simulate every step, and simulation grows as complex as the system itself. In these regimes, prediction is not difficult. It is provably impossible, not because we lack power, because mathematics forbids it. This is not speculation. Cellular automata, simple rule-based systems, already exhibit this behavior. From minimal instructions, they generate patterns whose long-term evolution cannot be predicted faster than running them. Nature, it turns out, often behaves like this. Biological development, neural activity, ecological dynamics, social cascades, all display irreducibility. They compress poorly. They resist theory. They outpace foresight. This shattered the final belief that given enough information and computation, any system could be predicted. In many cases, the future is not hidden. It does not exist in a compressed form at all. It must be generated step by step. Time itself becomes part of the computation. Artificial intelligence revealed the same limit from another angle. Machine learning models often outperform human forecasters, yet their predictions degrade rapidly outside narrow training regimes. Small shifts in data distributions produce catastrophic errors. Worse, many models exhibit overconfidence. They predict precisely and wrong. In finance, medical diagnosis, and climate modeling, black box systems sometimes perform worse than simple baselines when conditions change. In controlled tests, naive heuristics occasionally beat sophisticated algorithms. Here, complexity becomes liability. Models memorize the past but misread novelty. They fit noise. They hallucinate structure. And when reality departs from history, they fail. The most unsettling finding came when researchers compared models to chance itself. In certain high-dimensional systems, random predictors matched or exceeded structured models over long horizons, not because randomness is powerful, but because the system's future is effectively random relative to any compressed description. When the signal-to-noise ratio collapses, foresight evaporates. Prediction becomes theater. Numbers replace understanding. Confidence replaces accuracy. This forced an uncomfortable reevaluation. What exactly does it mean to predict? Traditionally, prediction implied causal understanding. To foresee was to grasp the mechanism. But now, prediction often relies on statistical correlations without explanation. And when these correlations fail, nothing remains. The model cannot repair itself. It does not know why it worked, only that it once did. In this regime, forecasting becomes fragile, sensitive to regime shifts, blind to structural change, vulnerable to feedback. This vulnerability is not accidental. It reflects a deeper truth. Many systems do not possess stable futures. They are path-dependent. History matters. Early accidents shape long-term outcomes. Slight perturbations rewrite trajectories. In such systems, the concept of the future dissolves. There is no single path to foresee, only branching possibilities. Prediction at best becomes probability, and probability itself becomes unstable. Distributions drift, variances explode, tail events dominate. The very notion of expectation loses meaning. At this point, the collapse is complete. Models no longer predict because the future is not statistically stationary, not computationally compressible, and not causally isolated. The assumptions beneath forecasting, linearity, independence, ergodicity, fail. And when they fail, chance re-enters, not as noise, but as benchmark. If a model cannot beat randomness, its authority vanishes. Yet this crisis is rarely acknowledged, because prediction is the public face of expertise. Governments depend on forecasts, markets depend on projections, institutions depend on planning. To admit that foresight has limits is to admit vulnerability, so the language softens. Uncertainty bands. Scenario analysis. Ensemble averages. The failure is reframed as humility, but the structural fact remains. In many domains, the future cannot be known in advance, not approximately, not probabilistically, not even qualitatively. It must be created. This forces a final philosophical reversal. Perhaps prediction was never the true test of understanding. Perhaps the universe is not designed to be forecast. Perhaps time is not a line waiting to be read, but a computation unfolding irreversibly. In such a world, models do not reveal destiny. They merely navigate. They guide action locally. They stabilize behavior temporarily. They do not unveil fate. And so, we arrive at the unsettling conclusion. When models predict less than chance, it is not because science has failed. It is because the universe has structure that resists foresight. Structure that generates novelty faster than reason can track. Structure that hides the future inside its own unfolding. Here, knowledge reaches its horizon, not at ignorance, but at irreversibility. The future, it turns out, may not be a secret waiting to be discovered, but something that does not exist yet in a form that reason can grasp. And when that is true, prediction ceases to be a window into reality. It becomes merely a tool for survival, a guide through darkness, not a map of what lies ahead. When a crisis threatens the foundations of a discipline, it rarely announces itself with alarms. It arrives quietly, not as contradiction, but as inconvenience, not as revolution, but as discomfort. The most dangerous failures are not those that shatter theories, but those that expose limits no one is prepared to face. The collapse of explanation, the rise of unexplainable patterns, and the failure of prediction did not go unnoticed inside research communities. On the contrary, they were documented meticulously in footnotes, appendices, technical journals, and conference proceedings that few outside narrow specialties ever read. The silence that followed was not ignorance. It was institutional. Modern science is not merely a method. It is a system, a network of universities, funding agencies, journals, review boards, tenure committees, and professional hierarchies. This system does not merely discover knowledge, it selects which knowledge is allowed to survive, and systems like organisms protect their own structure. The first pressure comes from funding. Research requires resources, and resources follow promise. Grant proposals must describe solvable problems, tractable methods, and predictable deliverables. They must assure committees that progress is possible, that results will justify investment, that uncertainty can be reduced. To propose that explanation itself has limits is to undermine the very premise of funding. A project that questions whether models can ever explain complex systems does not promise results. It promises doubt. Such proposals rarely survive review, not because reviewers are malicious, but because the institutional logic filters them out. Agencies are designed to fund progress, not foundational pessimism. Thus, researchers learn quickly what questions lead to careers and which lead to obscurity. The second pressure comes from publication. Scientific journals reward novelty within accepted frameworks. A paper must situate itself inside an existing literature, extend a model, refine a method, or apply a theory. Radical challenges to foundational assumptions face a brutal dilemma. If they are too technical, they are unread. If they are too philosophical, they are rejected as speculative. If they are too destabilizing, they are labeled unproductive. Peer review, intended to protect rigor, quietly enforces conformity. Reviewers are drawn from the very communities whose assumptions are being questioned. To approve a paper declaring limits of explanation is to cast doubt on one's own field. The safer path is to request revisions, more data, more simulations, more modest claims. The central doubt dissolves into technical detail, and the silence continues. The third pressure comes from careers. Academic survival depends on metrics. Publications, citations, grants, students, institutional reputation. Foundational skepticism produces few of these. A young researcher who questions the explanatory power of models risks being labeled unfocused, pessimistic, or philosophical. Such labels are fatal early in a career. Promotion committees reward productivity, not doubt. Tenure requires accumulation, not destabilization. And so those who perceive the limits of reason often learn to remain silent, or to migrate into marginal disciplines where their insights lose institutional authority. Philosophy becomes the refuge, but philosophy within modern academia is increasingly isolated from empirical science. Its critiques circulate among specialists, rarely influencing method. Thus, the deepest questions about explanation are exiled from the very disciplines they concern. A fourth pressure arises from pedagogy. Universities train students using stable narratives. Introductory textbooks present science as cumulative, coherent, and convergent. They emphasize triumphs, not limits. Anomalies are framed as puzzles awaiting resolution. Emergence is portrayed as exciting novelty, not epistemic failure. Chaos is introduced as curiosity, not catastrophe. The student is taught that deeper study will bring clarity, not that clarity may be unreachable. To teach otherwise would destabilize motivation. Why pursue years of training if understanding itself has a ceiling? Education, like funding, depends on hope. And so the curriculum preserves the image of a rational, transparent universe. The fifth and perhaps strongest pressure comes from public legitimacy. Science occupies a unique social position. It advises governments, guides policy, shapes technology, claims authority over truth. This authority rests on a single assumption that scientific knowledge is reliable, cumulative, and progressively closer to reality. To admit that many systems are fundamentally unexplainable or unpredictable would weaken this authority. How can institutions advise on climate, economics, health, or security if their own models have known structural limits? How can policymakers justify decisions if forecasts are unreliable? How can the public trust expertise if expertise itself confesses blindness? Thus, uncertainty is carefully managed, expressed in confidence intervals, hidden in supplementary material, framed as technical detail. The message remains optimistic. With more data, better models, stronger computation, the future will become clear. This optimism is not deception. It is survival. Institutions cannot function while publicly doubting their own epistemic foundations. And so the crisis fragments. Each discipline encounters its own anomalies. Physicists discuss irreducibility. Biologists discuss emergence. Economists discuss reflexivity. Computer scientists discuss interpretability. No unifying narrative emerges. No shared admission. The problem remains dispersed across vocabularies. This dispersion is crucial. As long as each field treats its limits as local complications, no one confronts the global implication that explanation itself may have structural boundaries. Occasionally, a voice attempts synthesis. A paper hints that reductionism has failed. A book suggests that complexity defies theory. A lecture proposes that prediction has intrinsic limits. These moments rarely spark revolutions. They become citations, footnotes, intellectual curiosities. The machine absorbs them and moves on. This is not censorship. It is selection. Institutions evolve to preserve stability. Ideas that threaten foundational narratives are naturally filtered out, not by conspiracy, but by incentives, by career pressures, by funding logic, by educational necessity, by political legitimacy. The silence, therefore, is not imposed. It emerges. And perhaps the deepest reason for the silence lies not in institutions, but in psychology. To accept limits of explanation is to confront a painful truth. Human identity is tied to understanding. We are the species that explains, that builds theories, that seeks meaning. The belief that the universe is intelligible sustains not only science, but self-worth. To admit that reality may exceed comprehension is to accept a form of cognitive finitude that feels dangerously close to insignificance. Researchers, like all humans, resist this. They prefer unsolved problems to unsolvable ones. They prefer complexity to opacity. They prefer temporary ignorance to permanent boundary. And so the narrative persists. Progress continues. Models improve. Computation accelerates. The anomalies accumulate quietly. The silence remains, but beneath it, something irreversible has happened. The limits of explanation are no longer speculative. They are mathematically formal, computationally proven, empirically encountered. Science has not failed. It has succeeded so deeply that it has discovered its own horizon. The tragedy is not that this horizon exists. It is that we lack the institutional language to speak of it openly. And until that language emerges, the crisis will remain what it is today. Not a scandal, not a controversy, but a quiet, disciplined, carefully maintained silence. A silence not born of ignorance. For much of history, humanity believed that understanding was not merely possible, but inevitable. That the universe, however complex, was structured in such a way that the human mind could eventually decipher it. This belief was not only scientific, it was moral. It suggested that reason had a privileged relationship with reality, that clarity was not an accident, but a right. The success of early science reinforced this conviction. From celestial mechanics to classical thermodynamics, the universe appeared orderly, law-governed, and transparent to rational inquiry. Nature behaved like a vast machine, intricate but legible. Every mystery seemed temporary, every anomaly a future triumph. And, quietly, without announcement, that confidence became an assumption. That assumption now stands exposed. The failures of explanation, the rise of unexplainable patterns, the collapse of prediction, and the institutional silence all point toward a deeper possibility, one that many researchers resist not because it lacks evidence, but because it lacks comfort. The universe may not be designed to be understood, not hostile, not chaotic, simply indifferent to our demand for clarity. This indifference becomes visible the moment we abandon the belief that logic is universal. Human reasoning evolved under narrow conditions, medium-scale environments, slow change, local causation. Survival required quick heuristics, not global coherence. Our minds learned to compress reality into narratives, categories, and chains of cause and effect. These tools are powerful. They are also provincial. At quantum scales, causality fractures. Particles do not occupy single states. Measurement alters being. Time behaves asymmetrically. Our intuitions, forged in macroscopic life, misfire completely. At cosmic scales, space curves, time dilates, horizons trap information. The universe expands faster than signals can travel. Vast regions are permanently inaccessible. Observation itself becomes limited by geometry. At biological and cognitive scales, emergence dominates. Consciousness arises from neurons without clear derivation. Intelligence forms from circuits without symbolic design. Identity persists through constant material replacement. Across these domains, the same pattern recurs. Human concepts fit poorly, not because reality is inconsistent, but because our cognitive architecture is mismatched to its deeper structure. This mismatch suggests a radical inversion. Instead of assuming that the universe is written in the language of logic, perhaps logic is written in the language of the universe, an adaptive tool, a local dialect, not a universal grammar. If this is true, then the failure of explanation is not a crisis of science. It is a revelation of scale. Our reasoning works where evolution prepared it to work. Beyond that, it degrades gracefully, then catastrophically. Mathematics confirms this suspicion. Gödel showed that no sufficiently rich logical system can prove all truths within itself. Turing showed that some problems cannot be decided by any algorithm. Chaitin showed that randomness infects even formal systems. These are not limits of technology. They are limits of structure. They imply that incompleteness is not a flaw, but a feature of rationality. Any system powerful enough to describe reality must contain truths it cannot derive. If logic itself is incomplete, what chance does it have against the universe? Physics adds its own boundary. Quantum mechanics forbids simultaneous precision of complementary variables. Relativity restricts information flow. Black holes erase data behind horizons. Entropy ensures irreversibility, not temporary ignorance, permanent constraint. There are things that cannot be known, not because we lack instruments, but because the universe forbids access. Information is lost, trajectories diverge, histories become unrecoverable. In such a cosmos, clarity is not the default state. It is an exception. Biology deepens the lesson. Evolution does not optimize for truth. It optimizes for survival. Perception filters reality aggressively. Vision discards most wavelengths. Hearing compresses frequencies. Attention selects fragments. Memory reconstructs rather than records. The world we experience is not the world as it is, but the world as it is useful. This means that even our most basic intuitions about space, time, objecthood, and causality are evolutionary artifacts, effective, efficient, but not necessarily accurate. When science pushes beyond these intuitions, it does not merely refine them, it often breaks them. Reality ceases to resemble experience, and the deeper we go, the stranger it becomes. This strangeness is not accidental. It reflects the fact that we are not the measure of the universe. We are one pattern within it, bounded, biased, finite. And perhaps the deepest misunderstanding of modern thought lies here: the belief that intelligibility is a property of reality, that clarity is built into the world, that confusion signals error. But what if intelligibility is a property of minds? What if clarity arises only when the structure of the observer matches the structure of the observed? In that case, opacity is not a defect. It is a mismatch. The universe does not owe us transparency. It does not owe us explanation. It does not owe us comprehension. It simply is. This realization transforms the meaning of science. Science is no longer a quest for ultimate truth. It becomes a strategy for limited navigation. We build models not because they mirror reality, but because they allow intervention. We accept theories not because they are final, but because they work locally. We pursue understanding not because it is guaranteed, but because it is sometimes possible. This is not defeat. It is maturity. To recognize limits is not to abandon inquiry. It is to refine it. But it does force a painful humility. The dream of a final theory, a single equation from which all phenomena can be derived, begins to look naive, not because we lack ingenuity, but because the universe may not admit such compression. Reality may be irreducibly layered, each scale governed by its own effective laws, each domain partially autonomous. No master code, no ultimate explanation, only a hierarchy of approximations, useful, accurate, incomplete. In such a universe, meaning itself becomes provisional. We explain until explanation breaks. We predict until prediction fails. We understand until understanding dissolves into pattern. Beyond that boundary, we operate without insight. And perhaps this is the final unsettling consequence. If the universe does not owe us clarity, then ignorance is not merely temporary. Some questions will remain permanently unanswered, not hidden, not mysterious, but structurally inaccessible. This does not render science futile, it renders it honest. The goal shifts from total comprehension to adaptive coherence, from final truth to workable models, from certainty to disciplined uncertainty. And here, paradoxically, a new dignity emerges. We are not the masters of reality. We are participants within it, finite minds navigating an infinite process, capable of extraordinary insight, yet forever bounded by the very structures that allow us to think. The universe, it seems, is not a puzzle waiting to be solved. It is a system unfolding according to principles deeper than human reason. We can trace its edges, map its regularities, harness its forces, but we may never possess it conceptually. And perhaps that is not a tragedy. Perhaps it is a reminder that clarity is not a right, that understanding is a privilege, and that the silence we encounter at the frontiers of knowledge is not a failure of science, but a signature of a universe that does not owe us anything at all. When the limits of logic become undeniable, a profound question emerges. If reason cannot fully explain reality, if patterns resist derivation, if prediction collapses, and if the universe does not owe us clarity, then what remains of knowledge itself? This is not a rhetorical crisis. It is an existential one. For centuries, knowledge was defined by explanation. To know something meant to grasp its causes, derive its behavior, and predict its future. Truth was something that could be written, formalized, and proven. Logic was not merely a tool, it was the foundation upon which certainty stood. But the edifice has cracked, not suddenly, gradually. Through irreducibility, emergence, incompleteness, chaos, reflexivity, and opacity. The question is no longer whether logic has limits. It is how knowledge survives once those limits are accepted. The first transformation is conceptual. Knowledge must detach itself from the illusion of finality. Instead of aiming at ultimate explanations, it becomes layered, contextual, scale-dependent. A theory is no longer expected to explain everything, only to function within a domain. Quantum mechanics governs the small, relativity governs the large, thermodynamics governs the many, biology governs the living, psychology governs the mind. No level reduces cleanly to another. Each possesses its own laws, its own primitives, its own irreducible structures. Knowledge becomes plural, not one system, but a hierarchy of effective descriptions, each incomplete, each valid. This pluralism is not weakness. It is necessity, because a universe that resists compression demands many lenses. The second transformation is methodological. Explanation yields ground to modeling. Instead of deriving behavior from first principles, we construct systems that reproduce it. Simulations replace equations. Statistical inference replaces deduction. Learning replaces reasoning. These methods do not claim truth. They claim performance. They are judged not by elegance, but by robustness. Not by insight, but by reliability. A climate model need not explain every atmospheric interaction. It need only forecast within acceptable bounds. A neural network need not represent cognition. It need only diagnose disease. Utility replaces understanding as the primary criterion. This shift is already complete. Most modern science operates in this mode, but its philosophical implications remain underappreciated. Knowledge becomes instrumental. A map, not a mirror. A guide, not a revelation. The third transformation is epistemic. Certainty disappears. In its place emerges probability, confidence intervals, ensembles, Bayesian updates. Knowledge becomes inherently uncertain, not because data is scarce, but because structure itself is unstable. We no longer ask, is this true? We ask, how reliable is this under these conditions? Truth becomes conditional, context-bound, revisable, not a destination, a moving frontier. This uncertainty is not a flaw. It reflects reality. In a universe of branching futures, path dependence, and irreversibility, knowledge cannot be static. It must adapt continuously. The fourth transformation is ethical. Once we abandon the dream of complete understanding, responsibility increases. When models are opaque, decisions become risk-laden. When predictions are fragile, policies become experiments. When causality is unclear, intervention becomes hazardous. The myth of certainty once shielded institutions. Errors could be blamed on noise, failures on ignorance. But in a world where limits are known, ignorance becomes culpable. Humility becomes an ethical obligation. To act while knowing one does not fully understand is a moral burden. Science becomes not only a technical enterprise, but a normative one. How much uncertainty is acceptable? How much opacity tolerable? How much risk justifiable? These questions replace the old metaphysical ones. The fifth transformation is existential. If logic is not sovereign, then meaning is no longer anchored in explanation. For centuries, understanding promised purpose. To know the laws of nature was to glimpse order, intention, design. But in a universe that resists logic, meaning must arise elsewhere, not from final causes, but from coherence, from usefulness, from survival, from narrative. Humans continue to seek meaning, but now in provisional structures. Values replace truths. Stories replace laws. Frameworks replace foundations. This does not degrade knowledge, it humanizes it. We acknowledge that we are not outside the universe, decoding it from above. We are inside it, constructing interpretations that allow us to function. Knowledge becomes a relationship between observer and observed, between model and world, between action and consequence. And here, a new definition emerges. Knowledge is not a mirror of reality. It is an interface, a compression that allows finite minds to navigate infinite complexity. It filters abstracts, approximates, and stabilizes, not to reveal essence, but to enable action. This redefinition dissolves an ancient confusion. The goal of knowledge is not to possess reality, it is to survive within it. The sixth transformation concerns the future of inquiry. If ultimate explanation is unreachable, what guides research? Not final theories, but boundary exploration. We search not for total laws, but for limits, where prediction fails, where emergence begins, where computation explodes, where causality dissolves. These frontiers become the true laboratories of modern science, not because they promise closure, but because they reveal structure. Understanding now advances by mapping impossibilities, by charting where knowledge breaks, by identifying irreducible domains, by formalizing ignorance. Paradoxically, this deepens science. A discipline aware of its limits is more precise, not less. It distinguishes solvable from unsolvable, predictable from unpredictable, explainable from irreducible, and in doing so, it becomes more honest. Finally, a deeper possibility appears. Perhaps logic was never meant to dominate knowledge. Perhaps it is one mode among many, alongside intuition, simulation, analogy, narrative, embodiment. Biological cognition does not reason deductively most of the time. It recognizes patterns, adapts, learns, anticipates. These are forms of knowing not captured by formal logic. Artificial intelligence, ironically, is rediscovering them. Learning systems outperform reasoning systems. Optimization outpaces deduction. Pattern recognition eclipses explanation. The future of knowledge may therefore be hybrid, part logical, part statistical, part experiential, part narrative, not unified, not complete, but functional. In such a future, the old hierarchy collapses. Logic is no longer king. It becomes advisor, a powerful tool within a larger ecology of cognition. And so, we arrive at the final insight. After logic, knowledge does not vanish. It transforms. It sheds the illusion of finality. It abandons the fantasy of total explanation. It accepts incompleteness as structure, opacity as boundary, uncertainty as condition. What remains is not despair. It is a more resilient form of understanding, one that knows its limits, one that navigates rather than conquers, one that treats truth not as possession, but as approximation. The universe, it seems, will never be fully known, but within that constraint, extraordinary knowledge remains possible. We can map galaxies, decode genomes, build machines that learn, heal diseases, predict storms, stabilize networks, not because we understand everything, but because partial understanding is enough. And perhaps this is the final reconciliation. Logic did not fail. It simply revealed its domain. Beyond it lies not ignorance, but a different landscape of knowing, where certainty fades, where explanation fragments, where models guide, where humility governs, and where knowledge, stripped of its ancient pride, becomes what it may have always been meant to be, not a path to omniscience, but a fragile, powerful instrument for living inside a universe that will always exceed us.